So yeah, more or less this part of code and the need for coloring is a subcomponent for the automatic differentiation that we need when we evaluate nonlinear function, the derivative of nonlinear function in JuMP. And more or less the code that we have in JuMP was implemented by Miles 8 or 9 years ago, even before when we were still MatPro based. And not many people touch it, and not many people do research on it, but we have new things to work on these things. And I will explain what potentially can be improved in JuMP to do better coloring and potentially have faster evaluation of derivatives in JuMP. So first, as explained, we need automatic differentiation in a few places. Why do you need it? For nonlinear optimization, we need it to find a way to compute efficiently sparse Jacobians and sparse Hessian of the Lagrangian. And to do that, we try to export the sparsity inside the structure to recover the full Hessian and the full Jacobian in only a few passes along the with directional derivatives. And I have a few figures after for that. And the final goal of this coloring and bicoloring is just to limit the number of AD passes in the expression tree. So let's show a few figures. So before that, the idea is when we have a function, we can, with the help of automatization, easily evaluate a product, a Jacobian vector product, or the transpose of the Jacobian times a vector product. And the idea is if we apply this product on each column of the identity matrix, we can recover all the Jacobians this way, but potentially if the Jacobian is sparse, we can recover multiple columns or rows of the Jacobian at the same time. And the idea is how can we compress as much as possible a Jacobian and Hessian to only recover the full Hessian of the full Jacobian on only a few products. That's the key idea of the coloring. So here is an example with only a simple Jacobian. So you can see on the left 4 by 5 Jacobian, and we can recover all the columns of the Jacobian in only a few directional derivatives along the direction E1 plus E2 plus E3, and the other one is E2 plus E3. And what we will do when we do that, in the first case we recover 3 columns, and the other one 2 columns. And after that, we have the compressed Jacobian. So when we have the 2 columns, the yellow and the blue one, and from then after we can do what we call a decompression and recover all the non-zero needed in a sparse Jacobian. So this is just a quick example how we can do column coloring. This is row coloring, same idea. It's just depending on the shape of the Jacobian, you want to use one or another. And the full workflow that we use, for example, in JuMP, is first we have the code to compute the derivatives. Then we found a coloring on it. We use the derivatives, and then we do the decompression. So I will not too much talk about the phase 1 and phase 3, which is the sparsity pattern detection and how we compute the derivatives in JuMP, but more about how we perform the coloring and how we perform the decompression. So after we computed the derivatives, how we recover where are located the non-zero in the compressed Jacobian relation. So the coloring is mostly related to graph theory, and we can see that as just finding an independent set and column, where, for example, if we represent from a graph angle, we have this kind of structure. So each column, when we do column coloring, can be seen as a vertex, and we have an edge between 2 vertex or 2 columns if we have a non-zero that is in common between these 2 columns. And here we have a few examples of what is the optimal solution. So potentially with 2 directional derivatives, we can recover all columns of the Jacobian. We can use 3, but it will be suboptimal. And the last one is a case where we do wrong coloring. For example, if we try to recover at the same time the column number 2 and the column number 4, we have an overlap with the first coefficient of the column, and we cannot do that. So this is the idea for the Jacobian. For the Hessian, it's a little bit more complex, but the idea is we relax a little bit the constraint about the fact that we can have an overlap on the same row, but as long as we have another way to recover it from the lower or upper triangular, we can do a coloring. So instead of having columns or rows that are independent, we want somehow a symmetric independency. So we have one way or another to recover the non-zeros. And for the symmetric coloring, we have two options, the star and the acyclic. And in JuMP, we only have one coloring, which is acyclic coloring. And it's important to understand the next part of the presentation. Okay, so this, what I explained, is more or less how coloring works. And for a long time, not many people did research on what we call bicoloring. So what is bicoloring? Bicoloring is just the use in the same times of row and column coloring. So for example, when you have a sparse Jacobian, which has dense row, dense columns, if you do a coloring, you will not have any gain because we cannot compress it. For example, if you have a dense row and you try to do column coloring, you cannot compress any columns because all columns share a common non-zero on the same position. And we have no gain to do that. Same thing when we have a dense column and we want to do row coloring, we have an overlap on each coefficient and we cannot compress anything. And the idea of bicoloring is how we can combine both coloring and at the same time both AD mode, forward and reverse, to try to compute with less AD computation all the sparse Jacobian. And this first example that I have in mind is a arrowhead matrix. So imagine that even if the pattern is symmetric, the non-zero are non-symmetric, so we cannot exploit any symmetry in terms of non-zeros. And you can see on the left and on the right that if we apply a row column coloring, we cannot do anything because each column or each row will have a different color because we cannot do any compression here. And if we use bicoloring, you can easily see that all the rows at the bottom can be recovered efficiently with the row coloring, and all columns on the right with the row column coloring, and those subcomponents can be recovered with row column coloring. And if we do that, we need way less AD passes to recover all the non-zero of the Jacobian. This kind of bicoloring was known since a long time, but not many software implementation were developed to solve this kind of problem. And when I tried to investigate how we can implement that, not many code were available online, and I said, can we use what was already implemented in the past? So people worked a lot in the past on this symmetric coloring because it was important to be able to compute efficiently sparse Hessian. And here, the key idea of all this research is, can we reformulate this problem of bicoloring as a symmetric coloring? So instead of seeing the problem from a graph angle, I found a solution from a linear algebra angle. Just before I explain the quick solution, this is another example when, for example, we have a sparsity pattern which is a rectangle, and here you can see also again that if you try to do compression along the row of the column, you have no advantages, but if you combine both row coloring and column coloring, with only 2 colors for the rows and 2 colors for the column, you can recover all the Jacobian. Okay. What time is it? I have time, okay. So this is also another example. So they explain if we have both a dense row and a dense column in your Jacobian, both of them, row column coloring will be useless, and bicoloring is the way to go. But potentially, if we only have a dense row or dense column, it can also make sense to use bicoloring. In the case, for example, of nonlinear least square, in general, the Jacobian has way more rows than columns, and because we have more rows and columns, it makes more sense from an AD point of view to use column coloring. But if a nonlinear least square problem, we have, for example, a constraint, like a normalization constraint, we can have a dense row, and in that case, we will need as much colors and directional derivatives as the number of columns of the Jacobian. And the idea is potentially we can just isolate these few constraints, which allow to not do a good column coloring, compute them with reverse differentiation, and isolate and remove this subset of dense rows and columns to efficiently compress the other part of the Jacobian. This was one example where barrel coloring makes sense also. The other one is the quite common equality constraint optimization. In this case, we expect in practice that we have a few constraints where we have way more input than output. And when we have that in practice, we want to use reverse differentiation. But if you have a dense column in the middle, it will kill all the advantages of row coloring. And in that case, we would like to isolate this dense column, compute it in a standalone way, and then do all the other computation with reverse differentiation. So this is another example where it makes sense to use bicoloring. So now the question is, how can we compute efficiently this bicoloring? And at the end, we can see some similarities between this bicoloring and the symmetric coloring. The first one is, in the case of bicoloring, we recover the non-zeros or from the column or from the rows. And in a symmetric coloring, we recover it from the lower or the upper triangular part. So can we find a way to make them both match? And the answer is yes, if we use an augmented structure like this. So we create a symmetry matrix. We will directly create the symmetry, the matrix H equals 0, J transpose J 0. And you can see that if you apply a symmetry coloring on this augmented matrix, you can directly recover bicoloring on it. That's very simple, but nobody think of that before. And as long as we can do symmetry coloring on the augmented system, we can directly have the bicoloring on the Jacobian directly. And here we can see something that starts to make sense for us in JuMP is you can see that we needed a color for each column and row of the augmented matrix. But at the end, we don't need this dark blue color. Potentially, we don't need to give any color for this column and row in the middle. So this component here, we don't need any color. We can use what we call a neutral color. And yes, so here we can
stand by the mic so that we can mix it up.
Okay, sorry. So here we have okay, here we can use a neutral color, and neutral color was used quite often in the past for bicoloring, but never used for symmetry coloring. In practice, we expect that in the Hessian, most of the diagonal is non-zero, and people say, okay, let's always assume that the diagonal is non-zero, and we don't take into account potentially diagonal of 0. But here, with this structure, the H on the top, all the diagonal is 0. And we investigate, because we want to realize symmetry coloring, which was initially designed for Hessian, what can we do if we have the diagonal of zeros? And we see that we found a few things that can be directly used now in JuMP when we do Hessian coloring. So the idea is, for the neutral colors, when we will do the decompression, we will check potentially if we need the color to recover diagonal coefficient. And if you don't need it for diagonal coefficient, we can potentially remove the color directly. We can neutralize it. And this is, inside the star and acyclic coloring, the key idea. So here, inside the acyclic and star coloring, without going too much into the details, inside this coloring, we rely on two kinds of structure, what we call the two colors stars and two colors tree. That's more or less what is generated inside these two coloring. And when we have different substructure, we need to recover the non-zeros in the sparse Hessian and sparse Jacobian, only the colors of the hub in the stars and the colors old node in the tree. But whenever we have a very simple trivial structure, we can choose whatever we want for the decompression. And from that, we can potentially discard some colors that we don't want. And by doing that, we can remove the number of colors needed, which lead to less directional derivatives and a faster evaluation of the sparse Jacobian and sparse Hessian. So from that, we did this Julia package with my colleague Guillaume Dalle. So we use all the previous paper on bad coloring, and we did a new one when we explain what we can do on bicoloring and what can be improved already on coloring and bicoloring. In terms of implementation, that's very simple. We just create a problem. We specified if we want a symmetric or non-symmetric structure, if we want to do bidirectional computation or only along the column or the rows. And once we do that, we perform the coloring. And from the coloring, after, we can directly do the compression and the decompression and recover the group of the color or what is the color of each column. So this is more or less the code, very simple. And also when we want, for example, inside an inner loop on an optimization solver, do new AD passes to compute the new non-zeros of a sparse Hessian and sparse Jacobian, and we can then update it. But now the main question for you here is, how can we use all these things in JuMP? And first of everything, we don't need any coloring for the Jacobian in JuMP, because we rely on something based on the expression tree, and because we have the expression tree, it will be very fast to compute the Jacobian this way. And also because we have a way to extract substructure inside the Jacobian, it will be act as a little bit checkpointing, so we don't need coloring for the Jacobian in JuMP, but we need it for the Hessian. And because of this connection between bicoloring and symmetry coloring, we found a way potentially to reduce the number of colors when we do coloring of the Hessian. So that's why I think it makes sense in the future to potentially check if we have non-zeros or not in the diagonal in JuMP, and potentially improve the sparsity pattern to not always assume that the diagonal of the Hessian are fully non-zero. So this is the first part about what we can improve in JuMP. The other one is, in JuMP, we only support the natural ordering of the vertices. What does it mean? It means that potentially when we do the graph, it's a greedy algorithm, so we will color step by step, and we start to do the coloring by starting by the first column or first row, and we continue to do the process this way. But potentially we can change the order in which we treat the vertices, and some versions are more relevant than another one. And for example, one ordering was proved in the paper of Kolpak, the ordering smaller last, give way better coloring. And it could make sense to improve JuMP to support other ordering. And what I have in mind also with different ordering is whenever we have a banded structure, which is a special case of chordal graph, we have a perfect ordering that can be potentially computed. So it means that we have a way to have the best possible coloring if we know that a graph satisfies a special structure. So if whenever in the future we support various vertex ordering, we can potentially detect the structure to be banded and have a more efficient coloring. Something else that could be also improved in JuMP is right now we only have acyclic coloring, but as I explained before, we have another symmetry coloring called the star coloring. The star coloring can, in practice, give more colors, so it requires more AD passes to recover all the non-zeros, but still has the advantage to not need to store all the compressed Hessian. And whenever we have a large problem and we need a lot of compressed column to store, it can blow up our memory, and at the end we cannot store it. And with the star coloring, we can one by one do the directional derivatives and do the decompression. So it will require way less memory, and it can be, as I said, relevant for very large problems. And the other thing that I check a little bit in the code is right now we depend on packages called datastructure.gl and a special int digent set, and I implemented a more efficient and smallest one in directly sparse metric coloring, and I think it could make sense for JuMP to just implement this small substructure and drop the dependency on data structure. It could help, I think. So this is another thing can be useful. Conclusion about what what we did in smart metric coloring can be used in JuMP. We can be smarter if we don't suppose that all the diagonalization is non-zero. We can gain something here. We can also potentially, as a pre-process phase, try to do coloring on a multiple ordering. So if we have a way to plug any vertex order, we can try to do the coloring for many other vertex order, and at the end keep the best one. In practice, doing a coloring is quite cheap. So doing it for multiple vertex ordering can help a lot after to have a fast evaluation of the derivatives. And potentially also for the user, he can try a few of them, and for a given problem, if he observes that the vertex ordering works better than the other one, keep it for the future. And yeah, what I can suggest is, can we potentially do an AD backend, a new AD backend, where we rely more on this package, or find a way to benchmark with what we have and what can bring on in JuMP. So this was the first part about the connection about coloring and JuMP and MY. Now, the other thing that is nice is how can we use JuMP to do coloring? And before I explain how we can do greedy coloring, so I mean, we have a graph algorithm. Now, the other way is how can we use optimization to find the coloring? And to do that, we can use more or less the recent API about constraint programming that Oscar probably worked on in JuMP. And this is a very simple model where with constraint programming, we can do the row or column coloring, so only for the Jacobian. And it's a very simple model, and from that, we can compute coloring. And in sparse metric coloring, we have an extension for JuMP and MOI, and instead of having a greedy coloring, we have an optimal coloring algorithm. We rely internally on minizenk, which can use inside IGS or CPSAT. We can also use a new routine that you added that is e-solved and feasible. So we use it directly in this code. And at the end, we can compute a coloring with as a constraint programming problem. So this is another way to compute it. So for sure, it's a difficult problem, but we can use a time limit and see if we can have a better solution than the greedy implementation of the coloring. And this package is registered and almost have no dependency, so quite easy to integrate in other packages.